help you understand how M-mode works. We have an ultrasound ray which is emitted, and if it hits a boundary of the heart, it gives a reflection. Another reflection here, another reflection here. But since the heart is moving, the boundary also moves, and therefore we have the typical M-mode tracing. Don't forget, this is the time axis, and this is the depth of the ultrasound. We can now delineate exactly which structures we see. Here we have the right ventricle. This would be this area here. This darker area is the septum. Here we have the cavity of the left ventricle, and here we have the posterior wall of the left ventricle. And we can see how the structure moves from diastole to systole. Even though M-mode is an old technique, it has a number of advantages. The first advantage is we have a very good time resolution. We can really see fast or quickly moving structures very nicely. Here is the aortic valve, and you can see the flutter motion of the cusps. The second advantage is we can really perform good measurements which involve timing of events, complex maybe to the beginning of the aortic valve opening and many other. And if you have a lot of experience, as many colleagues do who grew up with M-mode, then you can really get a lot out of this technique. So this is how you would get the M-mode for the measurements of the aorta and the left atrium. You can start out from a parasternal long axis view and perform the measurement, or you can also do it from a short axis view. I will show it to you from a short axis view. First of all, it's important to display the aortic valve in such a manner that you can see the leaflet or the cusps of the valve. And then you would put the M-mode through the aorta in such a way that you can recognize the opening and closure of the valve. Okay? This is the aortic root. You have systole starting here. It's very easy to see, first of all, the ECG. Second of all, you have the opening motion of the right coronary cusp. This is the right coronary cusp when it's open. So this is systole, and then you have diastole, backwards motion of the aortic root, and a closed aortic valve. What you can see very often is you see little fibrillations of the cusps, which is normal. Sometimes they're more, sometimes they're less. So this is not a pathologic finding. When we do the measurement, we perform the measurement exactly at end diastole, so shortly before the aortic valve opens. So this would exactly be the best point to do the measurement. Let me just go into the correct program. So leading edge, front of the aortic root, front of the back wall of the aortic root. And then to measure the left atrium, you would check for the region of the left atrium where it is largest. This is systole here, and again you would measure the left atrium here, and you would then get very similar measurements for the aorta and for the left atrium, in any case normal measurements.
What we do is we hit on your screen, there will be an M mode button or that you can do, and it will give you this line, and you take and you place that line where you want to get your sample, and so it's a sampling line essentially. And care about what's going on around the rest of the machine, but we want to know what's happening along this one line over time, or help us identify those structures. So like I said, this is the septal wall that we're seeing across here, and then this is the anterior mitral valve leaflet, and we can see what that is doing. We can see that it's coming up and it's actually slapping against that septal wall, coming down and have a relaxation phase. So this is often called, just in particular, the EPSS or endpoint septal separation. And is what you're doing is you're seeing the relaxation phase. So as the heart goes, finishes systole and is in early diastole, we see the heart, the mitral valve leaflet relaxes, lets in a large amount of blood, and that causes the mitral valve leaflet to hit the wall. As it relaxes, it comes down, and then we hit the active phase of diastole, and then we get a little bit more blood coming in, so that mitral valve flips open a little bit more, and then it relaxes, comes down, and then it's closed. And then it's going to go through that same process, relaxes, flips up, lets all the blood in, it slaps against that wall. And so this is a pretty normal looking mitral.
To perform an M-mode measurement of the left ventricle, you need a parasternal long or short axis view. You can actually do it from both. I will show you how to do it from the short axis. So the first thing you have to look into is if the ventricle is really round. This is important for the reasons already mentioned. So once you have a nice view of the left ventricle, you will put the M mode exactly through the middle of the left ventricle and optimize the image so that you have a very good contour, and then freeze the image and perform the measurement of the septum at diastole. So we have the biggest width of the left ventricle shortly before the QRS complex starts. So this is where you would start with your M-mode measurement of the septum. Then you would measure the end diastolic diameter, the posterior wall. Now all these measurements are diastole, and you would then perform the same measurements at systole for the end systolic diameter, for the posterior lateral wall, and these are the measurements basically that you would perform. It's good to quantify the thickness of the septum, for the left ventricular size, for left ventricular function, for pericardial effusion. You would see an echo-free space here, usually behind the left ventricle, and also to determine whether the contraction of the septum and the posterior wall is synchronous. So in situations where you have desynchronous contraction, for example in left bundle branch block, you would see abnormalities also in M mode.